Okay. Chapter 16, Section 2. I think we're going to learn about channels. I think we're going to learn about channels. I think we're going to learn about channels. This is using message passing to transfer data between threads. As somebody that used to program in Go, I've been waiting for this for a while just to figure out how Rust does it. Thank you. Thank you. Let's do this. One increasingly popular approach to ensuring safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here is the idea in a slogan from the Go language documentation. Do not communicate by sharing memory. Instead, share memory by communicating. One major tool Rust has for accomplishing message sending concurrency is the channel, a programming concept that Rust standard library provides an implementation of. You can imagine a channel in programming as being like a channel of water, such as a stream or a river. If you put something like a rubber duck or a boat into a stream, it will travel downstream to the end of the waterway. This is going over it. This is channels. This is what I was waiting for. Message passing. And they give the visual representation of how it is theoretically, where they use the duck, right? And you have a stream of water. You put a duck here, and then you're just passing the duck along down the stream. A channel in programming has two halves, a transmitter and a receiver. The transmitter half is the upstream location where you put rubber ducks into the river, and the receiver half is where the rubber ducks ends up downstream. One part of your code calls methods on the transmitter with the data you want to send, and another part checks the receiver end for arriving messages. A channel is said to be closed if either the transmitter or receiver half is dropped. Okay, so let's break this down, right? So a channel has two halves, right? It has a transmitter and it has a receiver. The transmitter half is where we put the rubber duck. So this is where the start is. That's where we put the information in, the start of the stream. And then the receiver part is where the ducks end up at the end of the stream. So you have the transmitter, you put the data in here, and then you have something that calls on the receiver that checks to see, oh, there's new data here, use it. And then you can just sort of replicate that process where you have transmitter, receiver, the data comes out of the receiver and you pass it into another transmitter and it goes down to another receiver all the way down the stream. Another concept they brought up is the concept of a channel being closed. So a channel is closed if either the transmitter or receiver has been dropped. And closed being that you can no longer send messages through. So if your transmitter is dropped, then the receiver can't receive a message. And alternatively, if your receiver is dropped, then your transmitter should not be able to send a message because it's not going to go anywhere. So yeah, if either of those are dropped, then we call the channel closed. We say it's closed. Here, we'll work up to a program that has one thread to generate values and send them down a channel, and another thread that will receive the values and print them out. We'll be sending simple values between threads using a channel to illustrate the feature. Once you're familiar with the technique, you could use channels to implement a chat system or a system where many threads perform parts of a calculation and send the parts to one thread that aggregates the results. First, in listing 16.6, we'll create a channel but not do anything with it. Note that this won't compile yet because Rust can't tell what type of values we want to send over the channel. Alright, so yeah, we're just creating a channel just to create a channel. That's the type of life we live. Use standard library, sync, and then MPSC, which I forgot what that stands for. It has like a term. Oh, they can explain it soon. Anyway, let's create this channel. We have a tuple. This is the transmitter, I believe, the TX, and then we have the receiver, which is RX, and we have that equal to the MPSC channel, and that's not going to compile, so we're not even going to try. We create a new channel using the MPSC channel function. MPSC stands for Multiple Producer Single Consumer. In short, the way Rust standard library implements channels means a channel can have multiple sending ends that produce values, but only one receiving end that consumes those values. Okay, so yeah, let's go back. So this name is Multiple Producer Single Consumer. And the reason they state it this way is because your transmitter can be used in different places, but you can only have one receiver for this channel. So you can have, let's say, part A, B, and C all have the same transmitter, but over here they all funnel to the same receiver. Imagine multiple streams flowing together into one big river. Everything sent down any of the streams will end up in one river at the end. We'll start with a single producer for now, but we'll add multiple producers when we get this example working. Okay, so we're going to start with one and then start adding multiple producers, transmitters. I'm just going to say MPSC instead of the full name. So the MPSC channel function returns a tuple, the first element of which is the sending end, and the second element is the receiving end. The abbreviations TX and RX are traditionally used in many fields for transmitter and receiver respectively. So we name our variables as such to indicate each end. We're using a let statement with a pattern that destructures the tuple. We'll discuss the use of patterns in let statements and destructuring in chapter 18. We're in chapter 16 now. Okay. Using a let statement this way is a convenient approach to extract the pieces of the tuple returned by the MPSC channel. So what they're stating here is that two things. This call to channel returns a tuple, which has a sender and a receiver. I was calling it transmitter, but it looks like they use sender as the official term. And the names, why we use TX and RX, which is just traditional in the field of transmitter and receiver. They traditionally mean that. Meh. Let's move the transmitting end into a spawn thread and have it send one string, so the spawn thread is communicating with the main thread, as shown in listing 16.7. This is like putting a rubber duck in a river upstream or sending a chat message from one thread to another. So let's see what they have here. We have our thread, we have our channel thingy, MPSC. We create the sender and receiver. We have our thread where we move the sender into here, and then we're sending values. Okay? We're currently not using, I don't even know if this is going to compile, but we're currently not using the received values. Let me just write this up real quick. Use standard library sync I wrote the same thing twice. They have it in order. Use standard library thread. Don't need that extra line there. And then here we have thread dot spawn. We're moving stuff into a closure. And then we have our closure. And in our closure, we're saying let the value equal string from hi. So we're creating a string value. And then we're putting that string in our sender. I'm sending it over the channel. value dot unwrap. And I'm curious to see whether or not this compiles, because we're not doing anything with the value. It kind of just stays there. And it does. It does. Huh. Good to know. I'm guessing it compiles because now it knows, the channel now knows what type it has, and it just deals with strings. Okay. Again, we're using the thread spawn to create a new thread, and then using move to move the transmitter into the closer, so the spawn thread owns the transmitter sender. The spawn thread needs to own the transmitting end of the channel to be able to send messages through the channel. The transmitting end has a send method that takes the value we want to send. The send method returns a result TE type. So if the receiving end has already been dropped and there's nowhere to send a value, the send operation will return an error. In this example, we're calling unwrap to panic in case of an error. But in a real application, we would handle it properly. Return to Chapter 9 to review strategy for proper error handling. Okay, so what they're saying here is that send, this call to send, is going to return a result, which either is going to have the item that you're sending or an error. And we called unwrap on it because if there's an error, we're just going to propagate it out. Not exactly proper error handling, but it's quick and dirty. The reason as to why it may error out is explained here. So if we send something, but the receiver, if the receiver has already been dropped, then we have nowhere to send this thing, and then we're going to get an error. In those cases is where this error happen, unwrap, and explode. Cool. In listing 16-8, we'll get the value from the receiving end of the channel in the main thread. This is like receiving the rubber duck from the water at the end of the river, or like getting a chat message. So it sounds like we're going to use the receiver. And thread, here we go. Added a new line. Let received equal Rx, which is the receiver. Received, and we're going to unwrap it, which is going to give us a string, and then we're going to print that string. Got received. Make sure that runs, and we got hi, which is the message that was sent, which is cool. We open a new thread. This is happening someplace else. We sent the message hi into the sender right here, and then in our main thread we received it, and then we printed it out. Aww. The receiving end of a channel has two useful methods, recv and try recv. We're using recv short for receive. I'm just gonna say receive, which will block the main thread's execution and wait until a value is sent down the channel. Once a value is sent, receive will return it in a result, where it has the type and an error. When the sending end of the channel closes, receive will return an error to signal that no more values will be coming. The try receive method doesn't block, but will instead return a result immediately. An OK value holding a message if one is available, and an error value if there aren't any messages at this time. Using try receive is useful if this thread has other work to do while waiting for messages. We could write a loop that calls try receive every so often, handles a message if one is available, and otherwise does other work for a little while until we start checking again. We use received in this example for simplicity. We don't have any other work for the main thread to do other than wait for messages, so blocking in the main thread is appropriate. When we run the code in listing 16-8, we'll see the value printed from the main thread. Got hi. Perfect. Which we have here. Channels and ownership transference. The ownership rules play a vital role in message sending because they help you write safe concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership throughout your programs. Let's do an experiment to show how channels and ownership work together to prevent problems. We'll try to use a val value in the spawn thread after we've sent it down the channel. Try compiling the code in listing 16-9 to see why this code isn't allowed. So let's read it first. We have our thread, we have our multiple producer, single consumer, MPSC, right? We have our transmitter, we have our receiver, we have our spawn thread, and we move everything into it. So we move the things it's using, this into here. We create the value, we send it down, and then after we send value, we try to print it. This doesn't work, because here we're moving the value from this thread to this thread. I see. So that's definitely fail. So yeah, let's try that out. I think it's just adding one line. So copy. Bam. Everything else is the same. And we see that the value was moved here. And we can't use the value after it's been moved. So exactly what we expected. Here we try to print val after we've sent it down the channel via tx.send. Allowing this would be a bad idea. Once a value has been sent to another thread, that thread could modify or drop it before we try to use the value again. Potentially, the other thread's modification could cause errors or unexpected results due to the inconsistent or non-existent data. However, Rust gives us an error if we try to compile the code in listing 16-9, which is the same error we saw down here. They showed more of it than I did, but more or less, val has been moved. Was moved here, cannot be used here. If you want to use it, maybe you could copy it. Meh. Our concurrency mistake has caused a compile time error. The send function takes ownership of its parameter, and when the value is moved, the receiver takes ownership of it. This stops us from accidentally using the value again after sending it. The ownership system checks that everything is okay. And I am happy that it does that, because a tired me would do something like this just because, just typing away. Sending multiple values and seeing the receiver waiting. The code in listing 16-8 compiled and ran, but it didn't clearly show us that two separate threads were talking to each other over the channel. In listing 16-10, we've made some modifications that will prove the code in listing 16-8 is running concurrently. This spawn thread will now send multiple messages and pause for a second between each message. So let's see what they have here. Thread, channel stuff, duration. We have the creation of the channel, transmitter, receiver. We have our closer, we have the thread, we're moving stuff into it. We're moving seemingly just the transmitter. Here we have multiple values now, where we have high from the thread, for in a vector. And over the for loop, we are sending the values. So we're sending them one at a time, and then we're waiting for a duration of 1 second. Thread.sleep. And then in the main thread, we're iterating over the receiver. So here, and we have received here. And then we're printing what we received. I see. And this is going to print all of these, so everything is waiting. Cool. Also, it's waiting without explicitly calling the receive method, which is nice. So let's write this out. First, let's get rid of this thing. You are no longer needed. You have been changed. here. Writing that vector might take a while, so let me just copy it. So we have our values, right? And then we have to create our for loop for value and vals. And then we take this send, we put it there because we send the value, and then we wait. Thread sleep, we pass in duration. I haven't imported duration yet, have I? I have not. So use standard library, time, duration, from seconds, passing 1. And at the very end, this gets deleted, and we have a new for loop. For received and the receiver, print line got received. All right, let's see what happens. Oh, that's kind of cute. Got high, got from, got the, got thread, and we waited a second. Okay, and then after everything was received, the program exited. I'm kind of curious as to how it knew when to exit. Because yes, we stopped sending values. Oh, I guess when the scope ended, this got closed, and as such, it knew that it was already over. Once the transmitter got closed, the channel was closed. So you're not receiving anything else. So it could just exit. That would make sense. Let's see what they say. Make this big. This time, the spawn thread has a vector of strings that we want to send to the main thread. We iterate over them, sending each individually, and pause between each by calling the thread sleep function with a duration value of 1 second. In the main thread, we're not calling the receive function explicitly anymore. Instead, we're treating Rx as an iterator. For each value received, we're printing it. When the channel is closed, iteration will end. And yeah, this is exactly what I thought was happening. So they know exactly what the code did, how we wrote it, the vector, the looping over everything, and the sleeping before sending each item, right? And they mentioned that we're no longer explicitly calling the receive. Instead, we're treating the Rx as an iterator, and it knows to stop when the channel is closed. And the channel closed because in the closure reached the end of it, end of scope, and at that point in time, the transmitter was then dropped. And once the transmitter was dropped, the channel was defined as closed, and then the receiver knew to exit. So that's kind of cool. When running the code in listing 16-10, you should see the following output with a 1 second pause. And we did. That happened. Because we don't have any code that pauses or delays in the for loop in the main thread, we can tell that the main thread is waiting to receive values from the spawn thread. Very true. Creating multiple producers by cloning the transmitter. Okay, this is it. This is the part we were waiting for. So earlier, we mentioned that the MPSC was an acronym for Multiple Producer, Single Consumer. Let's put the MPSC to use and expand the code in listing 16-10 to create multiple threads that all send values to the same receiver. We can do so by cloning the transmitting half of the channel, as shown in listing 16-11. So yeah, let's read through this real quick. This top is going to stay the same. We have our transmitter, we have our receiver, and then we clone it. We have transmitter 1, and transmitter 1 is going to be moved into this closure, which is high from the thread. Same thing as the last program, sleep, for loop, yada yada yada. Then we also create a second thread. And in this one, we use the original transmitter. I see. And then we only have one receiver. So more or less, this receiver knows that there are two transmitters. I'm guessing they're using a counter somewhere. And it waits for both of them to be closed before this closes. Okay. So let's write that out. So things that have changed. One, we're copying it. And that's it. Write that out just so I am used to it. We have let transmitter 1 equal MPSC sender clone, and then we pass a pointer to the sender that we're cloning. That's very explicit. I like it when it's explicit. And then in the first thread, we still have values. And in here, we're moving transmitter 1. And this hasn't really changed, right? From the thread, 1 second. No, this hasn't changed at all. What has changed is that we more or less copy this code and put different values in there. So copy, paste, and this is going to use the original transmitter. And you have things like more messages for you. And I think that's all the changes that were made. That should work. So let's test this out. The duration hasn't changed either, so they're kind of jumbled. It's not just one then the other. However, they might see it as one then the other. High, more, high. No, they got it intertwined as well. That's good to see. Okay. This time, before we create the first spawn thread, we call clone on the sending end of the channel. This will give us a new sending handle we can pass to the first spawn thread. We pass the original sending end of the channel to the second spawn thread. This gives us two threads, each sending different messages to the receiving end of the channel. When you run the code, your output should look something like this. And it does, just a little different, but yeah, more or less. Make this big. And last, well, 2 paragraphs. You might see the values in another order. It depends on your system. This is what makes concurrency interesting as well as difficult. If you experiment with thread sleep, giving it various values in the different threads, each run will be more non-deterministic and create different output each time. Now that we've looked at how channels work, let's look at a different method of concurrency. And with that, we have reached the end of the video. If you enjoyed the video, hit like, subscribe. Outside of that, till next time, peace.